Welcome to Alien Space Education. I'm sorry this episode's taken so long to get out. I'm trying to get back into a routine of making sure these get out better and faster and quicker for you guys. So I'd like to apologise first. So I hope that's okay. So this amazing episode is all about dark matter and dark energy, the invisible force that shapes our universe, not just our solar system, not just the galaxy, the universe. It's the stuff that's in between. It's really, really weird stuff and it's really, really fun. So it influences the structure and the fate of the universe. So it's very odd. So buckle in as we embark on this journey to unravel the secrets of these invisible forces. First thing we need to do is understand dark matter. Dark matter is an invisible compound component of the universe that does not emit, absorb, or reflect light. Although we can't see it directly, its presence is inferred from its gravitational effects on visible matter. Here's a closer look of how we know about dark matter. So what is it? Dark matter is a form of matter that makes about 27% of the universe. That's a huge amount. Unlike ordinary matter, which consists of photons, neutrons, and electrons, dark matter does not interact with electromagnetic forces. This means it does not produce light or other forms of radiation that makes it visible and detectable only through gravitational influences. Okay, so we can't use a magnet or the usual ways that we detect things. We have to use gravitational influences such as gravitational waves. This is how we explore. This is why understanding them is just as important. The existence of dark matter was first suggested in the early 20th century, so long ago, when astronomers noticed that galaxies were rotating at a speed that could not be explained by visible matter alone. The gravitational pull of dark matter helps hold the galaxies and galaxies clusters together, affecting their structures and dynamics. Basically, dark matter is the water that we see. So imagine you couldn't see water, but you could feel the forces. You could detect it through the gravitational wave. You could detect it when you dropped a stone in it. You'd see the waves go out and you'd see things change ever so slightly on the surface of the water. That's how we detect dark matter. We detect those slight waves, and that's what it is. But it's such a strong force, it's holding things together and stops them from pulling apart, going in. Yes, the galaxies do move as they move through the universe and everything like that, and Andromeda is moving closer to us. So there's a slight force moving things together. However, dark matter is like the water. We're on the surface of the water holding us, and when the waves hit, that's how we detect them, and that's how we know they're there. So how do we detect dark matter? Since dark matter does not interact with light, so you can't see it, if you shine a light, you see the light hitting the surface. Even dark matter, you shine a light on it, you don't see it. It's not there. Okay? That makes it extremely challenging. It's not impossible, it's just challenging. So in science, nothing is impossible. You just have to think outside the box. However, scientists use several indirect methods to study it. Gravitational effects is one. These is the primary method for detecting dark matter. It is thought that gravitational effects on visible matter observations of the galaxy rotation, the curvature, and the motion of galaxy clusters suggest the presence of an unseen mass. So it's like I said, it's like, look, if we're in little boats and we're on the water, take the water away, What's holding the boats there? We know there's something there, but we don't know what it is. So we think it's dark matter. The other thing, so it's gravitational effects, or we can detect that way. Another way is cosmic microwave background. Cosmic microwave background, or CMB, which you may see in some things, background, provides a snapshot of the early universe. Analyzing the CMB helps scientists understand the distribution of dark matter in the early universe. So when we're looking back to the early universe, we can see where there's matter, where there's galaxies and things like that. But the bit in between, we can see that. And that's dark matter. That's some of the dark matter we can detect. So that's all one way to do it. Another way is weak gravitational lensing. Dark matter can bend light from distant galaxies through a process known as gravitational lensing. By studying the distortion, astronomers can map the distribution of dark matter in galaxy clusters. So just like the Milky Way has a lot of different galaxies around us, it helps us by using the gravitational lensing to look at that, and then we look at other ones that are out there. Direct detection experiments. Now this is experiments, so we are still learning. Like I say, nothing's impossible. We can do it. Researchers are conducting experiments to detect dark matter particles directly. These experiments involve placing highly sensitive detectors deep underground, shield them from cosmic rays and other sources of interference. So I believe it's in China. They've dug a giant hole. They've gone into a mine. They dug down deeper. They put loads and loads of sensors all around, and then they filled it with water. A special water that has nothing in it. They make sure it's perfectly pure. That's it. And any movement has to be noted. So if there's an earthquake, it's going to be a big shake. But if it's a small movement, and we're talking microscopic movements, even smaller than that, it detects the slightest deviation. And that's how we're detecting it. Now, it's still ongoing and it's still experiments. There are some papers written about it, but these are the sort of experiments we're running. Yes, they cost billions and billions of pounds, but the only way to learn is to study and look and think outside the box of how do we detect something we can't see? Well, we have to look at different ways. What changes? And we know by weak gravitational lensing, it bends light. It distorts things. So we can use telescopes. But what type of telescopes? We need telescopes that detect light, but it can also detect the distortions. So we have to look at all different things. So moving on. Candidates for dark matter. Several theoretical candidates have been proposed for dark matter, including WIMPs, weakly interactive massive particles. WIMPs are one of the leading candidates for dark matter. They are predicted to interact via weak nuclear forces and gravity. Despite extensive search, WIMPs have not yet been directly detected. So in theory they're there, but we haven't found them yet. Axions. That's AXIONS. Axions are hypothetical elementary particles that could account for dark matter. They are predicted to be very light and interact very weakly with other particles. Hence why, going back to direct detection experiments, if dark matter is there and it interacts with the water, because we know exactly what water is, H2O, the slightest interaction, it can detect it. There are neutrinos. These are a type of neutrons that does not interact with standard weak interactions. They are another potential dark matter candidate, although their detection is challenging. It means it is extremely difficult to detect these. However, that is possible. Okay. Primordial black holes. Some theories suggest that black holes formed in the early universe that could make up dark matter. These black holes could be smaller and less massive than the stellar black holes, like the one at the center of our Milky Way or other black holes that we detect. So black holes could be creating something because we know they're pulling lots and lots of stuff, but what are they spewing out? Every action has an equal opposite reaction, remember, but we don't know. We know that black holes can burp stuff out, but that's matter. What about what we can't see? What's coming out of a black hole that we cannot see? So that's dark matter. There's a lot that we're still learning. There's different things there, and we are studying it very deeply. So what about dark energy? So we're going to shift our focus a little bit. It's a mysterious force that is driving the accelerated expansion of the universe. Unlike dark matter, which exerts gravitational attraction, dark energy appears to have the repulsive effects. And so why dark matter is pulling stuff in, dark energy is trying to pull it apart. So here's what we know about dark energy. Dark energy is thought to make up about 68% of the universe, a lot more of it. So that's why it's pulling us apart. That's why the universe is expanding. It is a form of energy that permeates all of the space and causes the expansion of the universe. Sorry, hang on a second. Causes the expansion of the universe to accelerate. The discovery of dark energy comes from observations of distant supernova in the late 1990s, which revealed that the rate of expansion of the universe is increasing. So we're looking at supernova back in the 1990s. We're in 2025 at the time of recording this. We're looking at how much that has changed. So therefore we know that dark energy is there, but because of that expansion, because of how it's going, we know dark energy is pushing things out further. The nature of dark energy remains one of the biggest mysteries in the cosmos. It could be a property of space itself or a manifestation of a new fundamental force. We didn't know about gravity till we discovered it. We knew it was there, but we didn't understand it. We don't understand. We know dark energy is there, but we don't understand it. So we're still learning. So how do we study something we can't see? Study of dark energy involves observing large-scale structures in the universe and its expansion history. So we're looking at things of how they expand. If you drop a pebble in water and see those waves go out, by learning how that wave goes out, we're learning how dark energy will work. It's a very simplified explanation, but that's what we're doing. So we look at things like a type LA supernovae. These exploded stars are used as standard candles to measure the distance of the universe. Observations of distance of supernovae revealed that the universe expansion rate is accelerating, leading to the concept of dark energy. What that's saying is you have two candles, and as the universe is expanding, they move apart. But as they move apart, we measure that distance. And it's getting further and further and further, faster and faster apart. That's what they're saying there. That is the concept of dark energy. Okay, we look at galaxy clusters, observation of dark galaxy clusters, and the distribution helps scientists understand the expansion rate of the universe and the effects of dark energy. So when we're looking at dark galaxy clusters, we're looking at how they move. Do they move around? Do they pull together? What's pulling them together? We know gravity, Andromeda, and Milky Way are pulling together, but we can't look at the Milky Way because we're in it. But we can look at Andromeda and look how it's coming closer and look at how it's moving closer. Is it coming round us? What's affecting it? We'll also look at the baryon acoustic oscillations. This technique involves studying the regular periodic fluctuations in the dense and visible baryonic matter of the universe. These oscillations serve as a cosmic ruler for measuring the expansion history of the universe. So we're looking back in time, we're looking further. So we're looking at this, how the universe has expanded and what effect that's having. And then we also have the Dark Energy Survey. This ongoing project aims to map the universe, measure the effects of dark energy by observing millions of galaxies and supernovae. So we're looking at everything. There's a lot that we're studying there just to study dark energy. And it means that some of the telescopes we have there that are mapping the night sky for us are looking at everything. And then when it's mapped to a certain area, we move on to the next area. But when we go back, we overlay the two and see what's moved. And it might only move a fraction of a millimeter in what we see. But that could be millions of light years away. And therefore, that fraction is a huge amount. So we're studying these very, very closely. The theories of dark energy, there's several. To propose to explain it. So we have the cosmological constant proposed by Albert Einstein. We're going all the way back to him. The cosmological constant is a form of dark energy that is constant throughout space and time. It represents consistent energy density filling space. Monologist. I apologize if I said that wrong. Albert Einstein was looking at this, and we're still learning. We have quintessence, a theory that suggests dark energy is a dynamic field that evolves over time rather than consistent. Quintessence involves a scalar field with varying energy densities. So why Albert Einstein said it's a consistent, quintessence says no, it's building over time. Modified gravitational theories, gravity theories. Some theories propose that dark energy could be the result of modifications to Albert Einstein's general theory of relativity. These theories suggest that the effects attributed to dark energy and could be due to a change of the laws of gravity at larger scales. So when you look at Albert Einstein and what he looked at Earth, the solar system, nothing too big, well, as big as he could imagine. But because we now know the universe is so much bigger than what he knew, maybe things are a little bit different. So the impact of dark matter and dark energy. Understanding these has some profound implications to our knowledge of the universe, the cosmic structure, and how evolution the universe is. Dark matter plays a crucial role in the formation of structures of galaxies and galaxy clusters. Its gravitational influence helps to shape the large-scale structures of the universe, guiding the formation of cosmic structures. Dark energy, on the other hand, affects the rate of expansion of the universe and its ultimate fate. The interplay between dark matter and dark energy influences the overall dynamics of evolution of the cosmos. Fundamental physics, the study of dark matter and dark energy, challenge our understanding of the fundamentals of physics. Dark matter could reveal new particles and forces, while dark energy might provide insight into the nature of space and time. Exploring the phenomenon could lead to breakthroughs in our understanding of the fundamental laws of nature and possibly the unification of the different forces in the universe. So understanding more about it will help us do other things and learn more. What further research there is and discoveries. Research into dark matter and dark energy is ongoing, with numerous experiments around the world, observations designed to shed light on these cosmic mysteries. Further advancements in technology such as more sensitive detectors, larger astronomical surveys, will help us probe deeper into the nature of dark matter and dark energy. The quest to understand these phenomena continues to push the boundaries of science and promises to reveal new and exciting insight into our universe. Because we're looking at how our universe was formed, we might be just one universe, or there could be other universes, and how they develop and how they evolve and how we look past our universe is still something that dark matter and dark energy could help with. So we're looking at how things are, how dark energy and dark matter could help us with that. The quest to understand these forms, so the current research and further directions, as we look further, several key research efforts and missions are focused on unraveling the mysteries of dark matter and dark energy. The Large Hadron Collider, or LHC, at CERN is searching for signs of dark matter through high-energy collisions. By studying particles produced by these collisions, scientists hope to detect dark matter candidates and gain insight into their properties. So the Large Hadron Collider is studying this, and they have created dark matter, very, very small particles of it, and we are studying it. But it's also creating new stuff as well. By throwing particles together, we're learning more all the time. The James Webb Telescope is set to explore the distant universe and observe the formation of galaxies. Its observations will provide valuable data into the distribution of dark matter and the effects of dark energy on the cosmos expansion. So like I said, it's looking at these images, but it does it in different wavelengths. So it sees pictures in different colors. And by looking at these things, we learn more. We have the Vera C. Rubin Observatory. This upcoming observatory will conduct large-scale survey of the night sky, mapping the distribution of galaxies and dark matter. It aims to provide new insight into the nature of dark energy and the structure of the universe. So we've got new things to discover and to look at. So we're doing a lot of work, despite the fact we don't know everything about it. We have direct detection experiments. Experiments such as the Lux Zeppelin and the Xenonic 1T are designed to detect dark matter particles directly. These experiments involve highly sensitive detectors deep underground to minimize the interference from other particles. There's a lot going on. And the main thing about scientists or astronomers is, if you don't know something, ask a question. And this is what we don't understand when we don't know dark matter and dark energy. So we ask the question, what is it? And as you can see through this whole podcast, that a lot of people around the world have said, we don't know either. All the way back to Albert Einstein, we don't know. So let's study it. So we can answer those questions. Just because you don't know doesn't mean you can't find out. It's really, really, really important that my listeners study and understand that the more you study, the more you learn, the more you understand different things, and the better life will be. And the better are the advancements of human science and our exploration of the universe will get as we learn more. As we wrap up our exploration of dark matter and dark energy, it's clear these cosmic phenomena are central to our understanding of the universe. Dark matter and dark energy are not just scientific curiosities, but fundamental components that shape the structure, evolution, and the ultimate fate of the cosmos. The quest to uncover the nature of these invisible forces challenges our knowledge and inspires new discoveries. As scientists continue to probe the depths of space and the fundamental laws of nature, we can look forward to exciting advancements and revelations about the universe. Thank you for joining me on this amazing episode of Alien Space Education. I hope you've enjoyed the journey into the mysteries of dark matter and dark energy. Please remember to subscribe, rate, leave your review, and check out my website, spaceforalleducation.com. If you have any questions, anything, please get in touch and we'll keep this going. And I will look forward to it. And I'll have another episode for you in the early year. Thank you.